Our next presenter is Kymani Brown. His presentation is called Thin Film Coatings on Additively Manufactured Components, and the faculty advisor is Dr. Tyagi. So, Kymani, go ahead and please share your screen.
Okay, so good afternoon, everyone. So Ms. Langford stated that the project is on tin film coatings, but we had to shift just a bit in order to understand the basic properties of previously printed AM parts, just to get a better understanding and formulate a reference point for where our new thin layer plated metal would be. Like, we need a reference point. We need to establish a reference point. So the topic of research is the effect of corrosion potential in AM-produced metals. My name is Kymani Brown, and my advisor is Dr. Pawan Tyagi. So just to go through a quick outline of what the research will be about, we'll just quickly go over an introduction, the aim of the study, short literature review, some research questions that I devised while going through, the methodology that I developed while going through as well, the results attained, and the conclusions drawn. So just to establish the general idea of what the study is about is corrosion. Corrosion is the deterioration of metals due to oxidation or due to just reacting with the air, various liquids, and oils on the surface of a metal. To get more specific, we're analyzing the corrosion potential in AM-produced parts. The corrosion potential is the rate at which the anodic reactions at the electrode equals the rate of the cathodic reactions at its electrode, resulting in no net current flow in or out of the electrode. Next, we'll be talking about galvanic corrosion, where on the right you can see reference to galvanic series chart, which will be referenced later on. But the galvanic corrosion is one in which one metal corrodes before another due to how reactive they are. Next, we'll discuss redox, which is the gain of electrons, and oxidation, which is the loss of electrons. So the aim of the study was to measure the corrosion potential of a metal 3D printed part or sample through electrochemical experimentation, determining the basic properties associated with this printed part. In analyzing a couple articles, for instance, Farid H. in 2019, his setup was quite similar to what we were doing, in that he utilized what is known as a 3-electrode setup in order to do his experimentation. However, in analyzing the corrosion potential, he used a different element, being zinc, and he utilized the method of electrodeposition, while we did not go there. Next article that I analyzed was one from Carlos M. Hunter and Steve Policastro, where they utilized they analyzed it in various environmental conditions. This was useful as the electrolyte used in our cell was 0.6 molar sodium chloride, which I'm not sure if most of you are familiar, but this is the condition or the molar content found in seawater. So this research might be helpful for naval research. So the research questions that I developed while going through was, will the sample corrode after cathodic and anodic reactions has taken place on the sample? What does the Tafel slope look like after these reactions have taken place? And will the equations differ if they are performed on a sample that has been chem polished or electropolished? Now, quick disclaimer, that we didn't get to do the chem polished or electropolished samples due to school being closed. However, we did get to analyze it for as produced AM parts. So the methodology. As you may see in brackets, we have sample preps. This is because the method was divided into two sections, one being sample preparation and the other being software and cell setup. So for sample prep, right, we have a sample that's very sensitive to the environmental conditions, being that oxide layers may form just by leaving it out in the air. So we had to perform what is known as organic cleaning on the sample. This involves having the sample being submerged in acetone and then sonicated for 5 minutes. Sonication is a process of using ultrasonic waves in order to further remove or assist the removal of impurities on a sample. Next, we submerge the sample into isopropyl alcohol and sonicate it once more for 5 minutes, which further helps to remove any impurities on the surface. Finally, we submerge the sample into deionized water, otherwise known as DI water, to reduce any oxidation layers on the surface. And to ensure consistency, after each sonication, the sample was rinsed in DI water. This is all an attempt to get a 1 centimeter square area of the sample clean enough to be tested. Here we have the materials or the necessary materials that have been listed being the electrochemical cell, the 0.6 molar sodium chloride, and the Princeton Applied Research versus that 4. To the top right-hand corner, we can observe the setup of the project being the working electrode where the sample is connected, the reference electrode being saturated KCl, and the counter electrode at the top right-hand corner. Now, this is where the galvanic series comes in. The counter electrode stands as a metal or an electrode that resists corrosion. In this cell setup, the sample electrode was platinum. I'm not sure if you can see the galvanic series chart, but as you can notice, platinum is at the lowest area, and the sample that we used was 316L steel. What this means is that the platinum was more noble, being rather less reactive than the sodium chloride, which is where the galvanic corrosion takes place, causing the 316L steel to corrode much faster or corrode more than the platinum. The next part, or the next area for methodology, is the software and cell setup. So the electrolyte utilized was 0.6 molar sodium chloride, and this was mixed or formulated in a 250 millimeter beaker, which was then poured into the cell and checked for any potential leaks. As you can see here, the cell was in a bigger container. This is because if the washer isn't set correctly where the sample is connected, then the electrolyte may leak out, leading to inaccurate results being obtained. After which, we connected the versostat power supply on the sample and added the reference electrode, or otherwise known as the saturated calomel electrode, and connected or set up the open circuit potential, OCP. The corrosion, the OCP setup was set for 64,800 seconds, which is exactly 18 hours. And when we were doing for the cathodic polarization scan, it was set for 0.1 volts plus the OCP realization period to negative 1.2 volts versus the saturated calomel electrode, otherwise known as the reference electrode. And when we were performing it for the anodic polarization scan, it ran from negative 1.2 volts plus the OCP realization period to 0.1 volts versus the reference electrode. So earlier, as I said, I mentioned OCP, open circuit potential. Just to note, the image on the right isn't a result, but it's just to establish a reference point so that everybody can kind of understand what I'm saying. So the OCP is a passive experiment, right? It is where the formation of oxide layers and removal of material takes place until it levels off to our desired potential. This is where voltage is measured with no current flowing through the cell. And for this example, they ran for 30 minutes. But as you can see, the graph lines began to level off, meaning quite a good OCP scan. Next, we did the cathodic polarization. This is where the potential of the cathode changes, and this reduces corrosion. And again, the galvanic potential changes for the sample as reduction takes place, meaning more electrons are gathered around the electrode. Next, we look at the anodic polarization. This is where the voltage this is where pits are developed due to the least positive current and voltage flowing in the cell on the metallic surface. They form what is known as pitting regions, and this creates what is known as the pitting potential, which is the point at which the anode begins to protect against corrosion. Also, during anodic polarization, oxidation occurs. Earlier, I mentioned the Taffy equation. This is derived from the Butler, Volmer equation, which is a linear approximation, which provides a point or a location for every single point along the curve of either the cathodic or anodic skin. It relates electrochemically the reactions and the overpotential. Overpotential being basically the cell voltage efficiency, and it is linked with the J naught value and the slope in the form of a line equation, which is y equal mx plus. Uh, so the results obtained from our research were, as you can see, the OCP scan produced what was a very stable with no drastic changes over an 18-hour realization period, which was pretty good actually. And our cathodic polarization scan at negative 0.2 volts produced a nice curve here. It must also be noted that the cathodic scan polarization scan was done multiple times while the anodic scan was not done as much because we decided to test for that at a bit later time, which we didn't have as much time to complete. Here you can see a graph showcasing where both the anodic and cathodic scans are present. The point, I'm not sure if you can see here, but the point that I'm highlighting with the mouse is where the two Taffy equations cross. This is known as the J0 area, which is where the point where oxidation, reduction both contribute to the reactions occurring in the solution. So to find this value, we equate both the anodic and cathodic Taffy equations, where we get x equals to negative 6.113 amperes. This is still in the form of ln J naught. So we perform simple mathematical calculations and we get the J naught value to be 2.21 times 10 to the negative 3 amperes. However, we need this with the current density as well. So we needed to divide it by 1,000 to get the centimeters squared. And that provided a value of 2.21 times 10 to the negative 8 amperes per centimeter squared. Next, we try to find the symmetry. The symmetry provides information about the point where neither oxidation nor reduction occurs in the solution. And this was found to be 0.139. So, from the results gathered, we came to the conclusion that the corrosion potential of a metal 3D printed sample was measured through the use of electrochemical experimentation. The Taffy equation of an as produced AM metal was determined for both the anodic and cathodic reactions. And it was also found that the cathodic polarization had a higher symmetry when compared to the anodic polarization. And finally, I would just like to acknowledge the Lockheed Martin Fellowship for giving me this opportunity, and also the University of the District of Columbia Nanotechnology Research Lab to provide me with the facilities required to complete this research. Dr. Pawan Tyagi for being a very good mentor and guiding me throughout the process. Giancarlo, Pius, Samba, Babukar, and Wadlison for giving their input in analyzing and making sense of all the data that I collect. Thank you. I hope that wasn't too fast, but I was trying to complete everything in the time.
I appreciate that. Any questions for him, please?
I had a question.
Okay.
Where do you see the real life application of your research?
So a lot of this research goes into naval use in terms of the material that they're using on the ships that go out at sea. So it's all an attempt to reduce the corrosion of the metal while out at sea, hence the use of the 0.6 molar sodium chloride because it mimics the exact conditions experienced while at sea.
Also, another question, where do you see like your next step of your research?
So this was in an attempt to establish the basic properties of a previously known AM produced metal. But the next step is to utilize nickel 2 sulfate to coat a copper layer to see how it behaves and then compare the results from that study to this study to see which is better, which provides I guess more resistance towards corrosion and how effective it is to manufacture and mass produce.
Thank you for the information.
Yeah, no problem.
Yeah, so Kymani, it's Dr. Tyagi here, and I just like to commend you for including the Staffel equation and analysis.
Yes, sir.
And actually, I taught this material into my senior level fuel cell class, and I'm glad you could collaborate with the PIS and like other graduate students and
Yes, sir.
learn this from them. So
Yes, sir.
very good.
They were very helpful.
Yeah.
Thank you.
Very good. Are there any other questions? Well,
Okay.
thank you very much, Kymani. This
No problem.
concludes our presentations today. Thank you all for joining us for the Lockheed Martin Research Fellowship Project presentations. We do have a website for this material, which I did include in the chat box. And do know that we have another 10 to 15 presenters for the fellowship. So hopefully in this summer, over the next few months, we will be scheduling those presentations. So thank you all again for joining us. The presenters were wonderful. Thank you. And faculty, thank you all very much. And most importantly, let's thank Mr. Derek McGowan from Lockheed Martin and Lockheed Martin for this wonderful fellowship opportunity. Thank you all. Look forward to joining you again